fellow programmers. Welcome back once more to this drives course. And today we're going to be reviewing and analyzing our brake resistance. Now, I had previously told you that this type of resistance are very popular in some applications. What type of applications, you might ask? Motion applications, vertical motion application or vertical movement applications like cranes, freight elevators, etc. Applications in which the inertia is pretty large as to stop on its own behalf. Let's say, for example, that if I wish to stop my motor and that it has a very heavy load in a time lapse of a short time lapse, for example, but beat by inertia. So what would happen here is we would need a brake resistance so that it can respect all that part that is regeneration, that regenerates, or anything that is overexceeded. So in our applications, generally for precision, I know that if I talk about position, we talk about motion control, but there's certain application that do require some precision. Some precision that we can simulate like a servo drive. But what is actually happening? For example, on the relay part, why do we really need them? What happens really? So whenever there's a load, and also we can add our gravity, then in this case, we can add larger inertia. And also, aside from us braking our relay and our crane, our elevator or our crane, we can start braking all of these, this elevator full of boxes. And at the moment when it spins or when it turns, it has to be the most exact motion as possible, and that it is supposed to take the necessary weight. Now, when we get these types of movements, at the moment of braking, there's an excess of energy. So that energy, we need to send it through a device. If not, what's going to happen is it's going to stop our motor, but through inertia and not because of a velocity ramp, which means that it's going to stop only until it's required. Okay, so if I wish to stop my crane, for example, let's suppose that there's a sensor here already, and when it detects this sensor while going down, how about if it stops braking little by little so that it has some deceleration time? And if we calculate so that it starts decelerating little by little, all the way until it gets to its limit, its set point. So if we say that if we start braking in 15 seconds, maybe it's because it's already calculated until it gets to this point. Or we can even add that whenever there's a signal, we can start changing its frequency so that it decreases. And once it gets here, then now it's going to be easier to brake, quicker. Okay? Now, what would happen if there's a larger load affecting gravity? And if I say that here, we can decrease its velocity, or that it directly brakes and for 15 seconds until it gets to this point. But like I said, inertia is even larger due to gravity, due to its weight. So then what's going to happen is that it's not really going to listen to it because inertia is already so excessive, so large, that what's going to happen is that it's going to go over. And it's not going to respect time or deceleration. So what might happen is that it's going to affect directly to the ground. Okay? So then it's going to damage my equipment. Same thing goes for this side. If we respect position, it's generally over a turntable. However, we're unable to see it from here. But it's turning every 90 degrees. Okay, so we might get, I don't know, a forklift to leave there a pallet full of boxes. But if you notice, it's turning every 90 degrees, but exactly. Because if not, it's going to lose its position. And it could even be turned away. And when carrying out its rollers, it might crash. So that's why I'm telling you about the position. So if it doesn't respect it, the inertia here is larger. And then that way it's going to be over. Do you notice? And it's also going to break through inertia and not by ramp. So if we wish to respect our deceleration ramp, and we wish to have a more exact brake, then that's where our brake resistance comes in. So we generate an excessive force of brake. And therefore, our drive is basically going to be blocked. It's going to stop our motor all the way until it's physically allowed to do so. So that's why we need to be very careful if we need the brake resistance or not. Okay? Now, what are we trying to do with our brake resistance? Well, that energy is we want to regenerate it. So it needs to be stored in some device, in some place. Okay, our typical energy phrase is energy is not created or destroyed, it's only transformed. So then, based on the need to regenerate energy in our drives, then that's when our motor rotor exceeds that velocity for our extractor. So then our motor is acting as our generator. And our brake resistance, which is also called dynamic resistance, is used when the brake path is much shorter. Now, how do they work? Well, what does it look like here? They basically look like this. Okay, so they have some lids, and those lids, if we were to remove them internally, they would have their different resistances in spiral. Now, these are all connected between them, and they work to store that energy, that electrical energy, or even to store that excessive energy. Now, little by little, this is going to start, it's going to start spreading out. Now, where are these connected? To our moves DC for our drive. And this spreads out the energy through heat. That's why we have our brake resistance. It's a bunch of coils in reality. Now, this drawing looks good, looks very good, very refined. But at the moment when we exceed our inertia, we generate an excessive amount of energy. And the only thing that our brake resistance does is get from that energy created or generated, is stored and displaced through resistance. That's basically it. Now, how is this connected? They generally have two cables, positive, negative, which is specified through every break resistance. And where are these connected then? On our drives, where they generally come in two ways, a positive or a negative. That's always. But next to them, we have a B1 or a B2. Now, also we have our very famous BR positive or BR negative. And that is basically it. What do you guys think? All applications need break resistance. Not all of them. The manual says all of them. But we should be able to know the difference if we need it or not, which is the same thing that I had previously told you. Okay? Because if this is a conveyor, you who actually need the brake resistance, do you think we're going to need it? Well, not really. So you basically need to analyze if this is needed or not. So these are pretty simple applications where there's no inertia and there's no position grade at the moment of braking, which is for our motor. We don't really use it. So industrial fans generate a huge amount of inertia, but only at the moment when they try to brake. But we need that they brake with precision. Yes or no? Not really. We use industrial fans every certain amount of permissions for our drive or for certain buttons or for certain amounts of time. But at the moment of braking, we generally brake through inertia. Okay? So we should analyze when this is necessary for our brake resistance to install or not, to be installed in our drive. Now, our terminals, there's two of them, BR positive and BR negative. So only follow the terminals and get those cables in there. Okay? So having said this, we are done with this topic. If you have any questions, write them down in the comments, and I'll see you guys in our next video.